Mm. Okay, thank you all for coming today, even though it's close to the holiday season. It's my pleasure to introduce our speaker, Ms. Yuxi Zhang. Yuxi is a PhD student at EPFL, working with Professor Alessandro Chiesa. She previously received a bachelor degree in mathematics from Princeton University. Her current research interests lie in theoretical computer science, particularly in probabilistic proofs, cryptography, and quantum computing. Today, she's going to share with us her recent work on how to prove post-quantum security for succinct non-interactive reductions. So without further ado, the stage is yours. Um,
Okay. Can you all hear me? Okay, good. Okay. So, yeah, really thank you all so much for coming. I know that it's close to the holiday time, and so I really hope that you could take something away from today's talk and that it will be worth your time. I'll try my best. So yeah, this is a joint work with Zhang, Zihan Hu, and my advisor Alessandro Chiesa. So this title has some really long name in it. So first of all, what are these objects that has such a long name? Um, oh, so I need to move to, yes. Okay, which, oh, I think because it's in presenter mode, I couldn't do that. Hmm? Oh, here. Where is it? Yeah, I can't see my cursor.
it's on all.
Oh, okay, I see. So, oh, okay, great. Yeah, and so first of all, what are these objects with really long names? Succinct non-interactive reductions. So before we talk about that, first, maybe let's look at a more well-known object known as succinct non-interactive arguments, or SNARGs. And it's basically a system between two parties, a prover and a verifier. And the prover may want to prove to the verifier some statement, for example, a statement about the graph G being three-colorable. And this natural way to do it could be just sending the coloring of the graph to the verifier. But the problem is coloring is too long. But if you're okay with sacrificing the information theoretic security, like you're okay with just being able to accept the proof correctly most of the time, then we can actually get a shorter proof. And that's where the succinctness comes from. Or more formally, what the prover does is it will take in some instance and witness as input, and it will try to prove to the verifier some statement that claims that an instance exists in the language of a relation. And it will send some short proof. Then the verifier will perform some checks and outputs a bit of either 0 or 1, signifying whether it accept or reject. So the SNARKs should satisfy a couple of properties. So first of all, it has to be complete, right? So if the graph is three-colorable, we want that the verifier to always accept. So you want honest prover to be always able to convince the verifier if it's an yes instance. And soundness says that if you have a no instance, then every efficient prover should not be able to convince the verifier, or it can only do so with some small probability. And succinctness acts that like this proof pi should be much shorter than the witness. And finally, we would also want ideally a stronger notion than this is like a strengthening of soundness, which is called knowledge soundness. And it says that every efficient prover that convinces the verifier should know a witness for the instance X, maybe only up to a small error kappa. So far, so good. Is there any question about this definition here? It's quite important since everything else that comes later will be built on this. So if there's anything unclear, you can tell me. Okay, I'm gonna take that as a yes. Okay, so these objects, they have lots of real-world applications. They're used in a lot of these companies and in blockchains, and it's something that is used a lot in applications, and which is exactly why it is important to understand its security. Though the object of our study today is something that is a generalization of the arguments. So it's something called a reduction. And here we still have the prover verifier, and they send some proof. Well, in addition to that, the prover also will output some new witness W prime, and verifier will output some new instance X prime. The idea is that instead of trying to convince the verifier of a statement that X is in some relation, the prover will try to reduce instance in a harder relation to an easier relation. So for example, this might be useful is, say you have n graphs or t graphs that are 3-colorable, and the prover wants to reduce the statement to a statement about just one graph being 3-colorable. So you can reduce the instance size with these objects. And then G is checked via other protocols. So these reductions can be composed sequentially. As before, as SNARGs should also satisfy completeness. I think for all yes instances, the honest verifier should make the verifier to output some new instance X prime that is also yes instance for the easier relation. And it should also satisfy soundness, meaning that for any no instance, every efficient prover will make the verifier output a no instance, unless with some small probability. And succinctness is the same. And finally, we also have the knowledge soundness. So every efficient prover that outputs a witness W prime for a yes instance, it must know also a witness for the old instance. It must know a witness for the harder relation. So is definition clear?
So you don't need the verifier to know if X prime is true or false. This is something like hidden from verifier.
Yes, it's about whether the reduction is correct. So if X is a true yes instance, then X prime should be a true instance for the honest prover. If X is a no instance, then this should be a no instance with high probability.
Yeah. With the standard non-interactive arguments. So for that, the verifier standard non-interactive arguments, he knows if the original X or the stated R is the ground truth, if X is true or false. But here, like no matter if it's true or false, he always outputs some X prime. This X prime doesn't tell him this.
Yeah, interesting. I think this will, the next point will answer this question. So because it's actually a generalization of SNARGs. So if you just take this R prime to be some trivial relation where X prime is 1, then this is essentially the same as SNARG. So if the verifier is only outputting 0 or 1, then it means that it kind of knows whether X is in the relation or not. But in the more general case, yes, it could just output any general X prime. And it doesn't know, it's like even in the original SNARK definition, it's not about the verifier knowing exactly. It's also a computational definition. So it's saying that the verifier will output, so if X is not in the language, it will only output 1 with very small probability. So it's not like it will know for sure. And
Well,
here
I
is
think
X
when
is,
saying it knows, I mean, up to computational
yeah,
bound.
yeah.
But I think I see the point. The point is you're saying basically I can modify the X prime. For example, if you give me a X, which is a graph, I could include a extra bit, for example, 1, indicating the prover's claim. The prover claims is a true instance, but the verifier doesn't need to believe it or not. Then I think later in the new instance X prime, you can also include a indicating a bit indicating if X prime is claimed to be true or false. I think you are saying that you can always modify this by modify structure of X prime.
Yeah. So it's definitely includes the case. It includes SNARK, right. By we just changing the relation somehow. And the second reason why these reductions are useful is because they're cheaper to construct than the SNARKs. So sometimes maybe you don't want to reduce all the way to either just outputting a 0 or 1. So you can just stop in the middle of a SNARK. And yes.
Go back to this one. It's on to so you are you familiar with?
Well, I do have questions. So
yeah.
She's introducing a new notion called succinct reductions. It's different from arguments. The only difference is you want to reduce the long statement X. At the end of the interaction, the verifier will offer some shorter new statement X. That's a new derivative is going to talk about. That's why I want to make sure that you understand this.
I actually do have questions. Sorry for the interruption. So you just mentioned that definitely cover the original one, but then you also mentioned that that's cheaper to construct.
Yes.
So yeah, that seems not matching. I mean, you're generalizing, but that's cheaper.
Well, it's generalizing in the sense that it includes the original SNARK definition. So any argument is also a reduction for the trivial relation when R prime is the trivial relation. So you can think of the SNRDX as maybe you have a full SNARG when you would reduce a statement like this to verify will only output a relation where this is just 0 or 1. But in the SNARK construction, perhaps you could stop earlier in so you don't need to output the final decision bit. Like maybe you just need to output a new graph that G, such that whenever all of those graphs are 3-colorable, this graph G is 3-colorable. But whether G itself is actually 3-colorable is then checked via other protocols.
This
is shorter.
As a notion you generalize, but as a construction you can sometimes skip some steps.
In the end of the day, it all depends like how do you define cheaper, right?
Well, I mean, as a immediate consequence, that means I have a more efficient way to construct the original thing. Like you generalize the original one, and that's cheaper.
It's not that. Okay, of course. So if the reduction is the original SNARK, it will not be cheaper. It will be the same. It's when it's not in the non-trivial case, then it's cheaper.
Yeah, so that's
sure.
I don't know why you cover that, but yeah, thank you.
Yeah, sorry. Yeah, I should say like non-trivial. Yeah, maybe.
Just say that it's useful or more general.
More general. I guess it's to lead to the next point, which is it actually has some additional applications compared to SNARKs. So it can also be packaged as accumulation schemes or folding schemes, yielding proof-carrying data like incrementally verifiable computation, and etc. So because of these additional applications, it is really interesting for us to study its post-quantum security. So just some examples of where reductions are used. Now, so where do these objects come from, the SNRGs or these succinct non-interactive reductions? There are a few places, and our focus today would be the hash-based SNRGs and reductions. In particular, these hash-based construction have a couple of advantages. They're efficient, they have public or transparent setup, and they're plausibly post-quantum secure. And this will be our focus today. So first, let's recall some how the hash-based SNRGs are constructed. So hash-based SNRGs are usually constructed using the BCS protocol. The BCS protocol involves two ingredients. So the first one is an interactive oracle proof, or IOP. So in the IOP, the prover again is trying to prove some statement to the verifier, and it will send over some oracle proof string. So, and then the verifier would respond with some uniformly sampled randomness. Then the prover will respond with the next proof string. The verifier again returns some random string, and so on and so forth. So at the end, the verifier could query these proof strings, pi1 to pi2 through all the way to pi k, at some location of its choice, depending on its randomness. And then it outputs a decision bit based on what it sees from the prover's queries, the prover's oracle proof strings. The second ingredient we need for constructing SNRG is some commitment scheme. And most often we're using Merkle commitment scheme. And as we all know, this is like the Merkle tree, how we build a Merkle tree. So you start from some long message, and then you hash all the way up to some root or the commitment here. And it allows you to open some specific location in your long proof message string. So if I want to open nth, and it will basically provide a opening proof for your location. So it will output these squares that are that allows you to later check if this is the correct opening. So with these two ingredients, it gives us a SNRG where the prover will send over a proof consisting of the commitments, the local openings, and opening proofs. So this BCS protocol is widely used in practice, and we know that it is secure classically in some ideal model known as the random oracle model. And the good news is it's also secure against quantum attackers. So CMS 19 showed that the BCS protocol is secure in the quantum random oracle model. Yeah.
So is this a knowledge or just argument?
Sorry.
It's an argument, or
yeah.
It's also an argument of knowledge.
So
in the classical setting, I think it's a thing, but in the post-quantum setting, do you actually prove this?
I don't think. Interesting. Perhaps they claimed it, but I think the knowledge soundness definition is not very straightforward. So like the knowledge definition, so actually knowledge soundness definition it requires some additional things.
Definition is the same, just how you prove it.
So actually I have some slides later about how you define knowledge soundness, but it's more, there's some like caveats in, yeah, we'll see. So that's true. So this is the case for SNRG. At least we know the soundness, not sure about knowledge soundness. And for reductions, we have the BMNW25. They extended the BCS protocols to also work for reductions. So it still uses the same second ingredient, but for the first ingredient, instead of the IOP, we have now an interactive oracle reduction. So again, the prover will try to reduce an instance of a harder relation to an instance in an easier relation. And the BCS protocol allows us, the extended BCS protocol allows us to construct a succinct non-interactive reduction. Where, so these recent works, they give some constructions of very simple and efficient hash-based reductions. And they show that these constructions are secure in the room. So they're secure classically. And the natural question we're asking here is whether these constructions are also secure in the Q room, so quantum random oracle models. Well, people believe that these constructions are also secure quantumly, but post-quantum secure. But this is never proven. This was never proven. So our work basically bridge the gap between this belief and the actual proof.
So I just want to clarify one thing. Previously, when you define the notion of reductions, you do require knowledge sounds. You know, like in your slides, you are defining knowledge sounds. So I'm gonna assume that when you say soundness for reductions, you mean knowledge sounds.
So
should I think this by default, or should I switch to?
Right. So yes, here I'm referring to they did show both soundness and knowledge soundness. Yes.
But when you ask this question.
Yeah, we did show the knowledge soundness. So yeah, here we're but the thing is, I will only present soundness in today's talk because the soundness proof. But in our paper, we actually showed knowledge soundness. Yes. Yeah, good point. Because actually there's some additional difficulties in proving knowledge soundness.
Yeah, I think extraction is a totally different story.
Yeah, exactly. That's where the definition is more difficult. So now why exactly does post-quantum security matters for these hash-based reductions? As I mentioned before, because they have these additional applications in hash-based accumulation folding schemes where you have lots of like recursive composition, and they're likely to be an important building block for the post-quantum redesigns of Ethereum. So since people are going to employ this more and more in the future, it will be interesting for us to study their post-quantum security. Now, as I mentioned, we have some post-quantum security results for SNARG. So why don't and SNARG is a special case of reduction. So why not just use the technique from the special case? Well, the answer is we cannot. And also maybe we should not. Because there are a couple of problems. So the first one is actually in CMS 19, they require the underlying IOP to satisfy some round by round knowledge soundness. Yeah, so I guess they did show knowledge soundness because and but the problem is that like the state-of-the-art IOPs and IORs, they don't satisfy this notion. They only satisfy some weaker variant of round-by-round soundness, knowledge soundness. And the second problem is that the result is about IOPs and not IORs. And even classically, the proof for BCS transformation, BCS security for IOR and IOP require different proofs. So quantumly, there's an even larger gap. Furthermore, they only showed non-depth security, and we would like a depth security. And finally, they adopt some like the usual quantum proof approach, like it's monolithic, and it looks nothing like the classical proof. But we would like some proof that uses some some classical intuition. In a sense, we would not only want a proof, we would like the right proof.
For problem 3, you mean in the class? Sorry, in the interactive in LP setting, we don't know any adaptive security proof.
that is true before our paper, actually,
Oh.
but it's not. I think it's not the main contribution. It's probably not extremely. It's not more difficult. It's probably like possible to just prove. Yeah. Okay, so now let's see how our results manage to kind of solve those problems. So our first theorem, first of all, in the classical case, they have some the BCS security. BCS security says the BCS soundness is basically the sum of the state restoration knowledge soundness of the IOR and the VC vector commitment extractability error. So the vector commitment is some abstraction of Merkle commitment, and our results is basically an analog of the classical case.
Sorry, what's the SRKX mean?
So it's state restoration knowledge soundness. So SR is state restoration. This is knowledge soundness.
Oh, okay.
Oh, sorry. Yes, true. Sorry, I will get to that very soon. It's basically some knowledge soundness definition for IOR, but we haven't introduced it yet.
Classical.
Yeah, this is classical, and we define some new quantum state restoration knowledge soundness notion. So that's PQSR. So in the left part, actually, we define both of these notions is our definition, and these new notions, why they make sense is because of the next two theorems. So like in the classical case, we actually know that state restoration knowledge soundness of the IOR is implied by the round-by-round knowledge soundness, and actually it's implied by the weaker variant, and it's like T plus K times the round-by-round soundness. And
What is P?
T is the query complexity, K is the round complexity of the IOR. So in our case, we also show that this implication works for our definition of the PQSR knowledge soundness. So basically, our definition is implied by some classical soundness definition. So by the round-by-round soundness definition. And so like here you have some quadratic speed up, and the intuition comes from Gruber's algorithm, and which we'll talk about next, so this step. And lastly, in the classical case, we know that Merkle tree has extractability error, t squared over 2 to the sigma. And in our case, we showed that Merkle tree has post-quantum extractability error of t cubed over 2 to the sigma. And this bound matches the collision error in BHT algorithm. But this is just the intuition about these bonds, like why we think our bond is asymptotically tight. So putting it all together, in the classical case, you have this bound for the BCS soundness error, and this is the bound we get for the post-quantum case. And so we believe that it is asymptotically tight, and that our bound has some pretty small constant in the O notation as well. Yeah, so so far so good, because I'm going to jump into the technical part. So if you have any question about any definition or our results, I could go back to some slides. I see some confused. Okay, that's good. Okay, so here's some more technical details. Okay, actually, sorry about this, but before I continue with more technical details, I actually need to introduce a bit more about the BCS transformation. So as mentioned, the security of the BCS transformation is proved under some ideal models. In the classical case, we had the random oracle models. So you're sampling a function uniform randomly. Then we are the adversary can make a query Q to the random oracle, and the random oracle responds with f of Q. In the quantum random oracle model, there's the only difference is that how the adversary's query access to the oracle. So now the adversary is able to make superposition query and get superpositional answers. So you have f of Q is going to be answered coherently. And with this ideal model, we call that the BCS protocol. In the BCS protocol, you're starting with an IOR, right? So IOR is something interactive, but the end result, the succinct non-interactive reduction, is non-interactive. So the idea is we need to use the random oracles somehow to make the IORs non-interactive. And how do we remove this interaction? Well, there's a well-known the Fisher-Shamir transformation, which allows us to remove the interaction. And also note that in this talk, I'm going to omit some more details about IOR, because actually in the IORs, the instances can include some oracles. So it means that there are parts of the instance where the verifier will only have oracle access to, like it will not be taken as input. It just introduces some more complexity to the proof, but I will not be focusing on it today. So with the Fisher-Shamir transformation, the end result is some like non-interactive protocol. So we have the Fisher-Shamir prover. It will simulate the IOR prover, and it will it will use the random functions to derive the randomness itself, instead of like using interaction and waiting for the verifier to give it randomness. And the way it does that is like, once the IOR prover sends some oracle proof string, it feeds it to the random function and use the random function to derive the randomness. And it does this every single round. So it then sends all the proof strings to the verifier. The verifier will then derive the randomnesses just like how the prover does it. And it then runs the IOR verifier with these derived randomness. There's a problem with this method. Do you see? So the problem is that if we send all the proof strings, it's actually too long. And that is why we need the second ingredient. So we need a vector commitment scheme. So the vector commitment scheme has some methods. It allows you to commit to a long proof string. And it allows you to open like some certain locations in the proof string locally. And the open also outputs the opening proof for these local openings. Then VC check allows you to check if the opening proofs are correct. So now with the second ingredient, we can combining these two together, we get something like this, where the prover is sending over the commitments and the verifier is sending back the randomness. And in the end, the prover sends over the local openings and opening proofs. So this is still interactive, but with Fisher-Shamir transformation, we get the final succinct non-interactive reduction. Any question about this transformation? Yeah.
Make it too long.
So it's using the second ingredient, the vector commitment scheme. So like instead of sending all of the proof string it's sending only the commitments. And it's only sending the openings that the verifier needs. So the proof string itself is long, but once you commit it, you can imagine all of these things are short.
Well, in this scheme,
scheme is first proposed by BCF for IOP, and then BM and W proved it that works for IOR as well.
Exactly. Yes. Yeah, there are a lot of details I'm omitting here, but it's like the big picture would be like this. And yeah, it's great because it's now succinct. So notice that there are two potential attacks for this transformation. So the first one is this adversary, it could query these oracles many times to get the verifier randomness that makes the IOR verifier output a yes instance. So like it could, in the Fisher-Shamir transformation, it could query many times to get kind of the best verifier randomness, since like the protocol is now non-interactive. And secondly, the prover can attack the VC commitment scheme using some ends that is inconsistent with the commitment. So it's basically you have like two types of errors, kind of. So you have the FS error and you have the VC error from basically this like two parts of the construction. Yeah. And this is kind of how our proof is structured. It's like we, again, today we will only focus on soundness. And the first part is kind of the Fisher-Shamir error. And the second part is the VC error. So our final result is saying roughly that BCS error is equal to the sum of FS error plus VC error, also in the post-quantum case. And notice that here, this post-quantum state restoration soundness definition is kind of the midpoint of our proof. So we would like it to be weak enough so that from here to here, you only have the FS error. And from this step to this step, it only has it only has the VC error. And you would also like it to be able, okay, so basically we want to find the right middle point in our proof. So exactly how can we define this post-quantum state restoration game to separate these two errors nicely? Well, to see that, first maybe let's recall how the state restoration work classically. So the classical state restoration soundness error captures the Fisher-Shamir. It's basically the soundness error of the Fisher-Shamir transformation. And the way it works is you have some classical adversary is querying all of these random oracles, and it could query any one of them. And it can make T moves. So each time it can query a different one. And then at the end, it outputs something that it thinks will give it the best verifier randomness. So it outputs some X and K proof strings that will maximize its winning probability. Then the FS verifier takes in these outputs and it computes the verifier randomness for the IOR. It runs the IOR with these computed randomness and it outputs the new instance. And the soundness is saying that a T-proof move SR prover cannot output something that reduces a no instance to a yes instance, except with some small probability.
Oh, sorry.
Yes.
Why you have K oracles? I think I missed this one.
So it's usually you have a different Fisher-Shamir oracle for each round of the IOR. So each Fi is the FS oracle for the ith round in the IOR.
Is this also true in LP?
Yes, because usually, like at least in our version, even the input size will be different, because in the first round you're basically hashing the current transcript, so your transcript has seen so far. Yeah. but it's usually you can just use domain separation. So it could be like derived from one random oracle. They could be derived from just one, and maybe you just take the first, like they just have different
If you
influence.
take one oracle for each round,
Yeah.
you have a K.
Yeah, K rounds.
Then what do you mean by T classical moves?
This is something that's related to the query complexity. So it's just something that the stereoisomation error depends on.
Perform before we output the final.
Yes, so it's number of query I perform, but it could just make 0 query to some oracle. That's possible. Yes. Then in our post-quantum definition, mostly nothing changed, but now the adversary's query is different. So it can now make quantum queries to these K oracles. So it can make T quantum moves now, but and after these T quantum moves, it's still outputting a final classical output. So the final output is still classical. Yeah, and this seems quite straightforward, but actually, if the stereoisomation prover has quantum power, what if it can? So here in the picture, we're drawing in a way so that it seems that it's always querying a superpositional query of only to the ith oracle. But what if it queries multiple oracles all at once? So it could query like a superposition query to multiple oracles at once. So our final definition also captured this kind of queries. And secondly, this definition is a quantum property. It seems pretty difficult to determine whether an IOR satisfies PQSR or not. So the question is if we could connect it with an easier classical property. So you can actually show that the IOR has that classical property, which implies that it is PQSR secure.
I think I missed the difference between classical and quantum. What do you mean by query all the classicals equal?
So it's like here it seems that you're only querying. It seems that you're only querying a superpositional query such that like they're all to the ith oracle, but it could be that it's like it's a sum of maybe the first query is just x comma pi 1, so it's to the f1 oracle, and then you have x comma like pi 1 and pi 2, so it's to the second oracle. So it could be a superpositional query to multiple oracles at the same time.
I think it's more like a definitional issue. Like in your definition, you really treat these different oracles as different. But in implementation, actually, you are just using one random oracle, probably with some padding.
Yeah.
I mean, you can always view this oracle as one single.
Yeah. Eventually, it is just some definitional difference. The difference is if we treat it, the problem is that, like, if you consider these move and query complexity not in a careful way, the final bound will have maybe some additional k factor. So, like, you have a multiplicative factor of k. You actually need to think about how much weight is distributed to each oracle.
Even classical setting, when you are showing the classical sounds error, in that one, can you treat all the oracles as a single oracle?
No, we're usually not doing that either. We're usually treating them all as separate oracles. It gives some more precise bound, I think.
I'm not sure if that's his question, but when you say you still do different oracle, do you mean even if you collapse everything to a single oracle by domain separation, the result, the tightness will still be the same?
No, I think that will be fine. But yeah, that will be fine.
Still be fine for yeah, how do that?
Oh, yeah, that right, but I think our eventually like our query model is kind of similar to, it's basically use like how you would do domain separation explicitly. Like the adversary will have some index I, which like it will have an additional index register which specifies which oracle is querying, and you count the moves, or like you don't use that move, but you prove some query bounds according to how much weight is distributed to the oracle according to like the amplitude squared of the index register I. Don't know if that makes sense. So it's like
I asked the question back, so
yeah.
So it seems your assessment you need to, I mean the take-home message you need to be careful, otherwise you will produce it better. But like, is it like easier to do in the classical setting or what?
Yeah, it's definitely easier to do in the classical setting because it's not possible to query all of the oracles at once, like in a superpositional way.
So,
yeah. So you need some actually we need some superpositional query model.
I'm not sure.
Yeah.
You said in a classical setting, there are two ways to view these oracles. First way is view them as different oracles. The other way is just do the domain separation as you explained. One query is counted as a indicator at the beginning and then the actual query. I feel these 2 point of views give you the same bound, but you claim there should be one point of view will give you an extra K factor. That I don't understand. Just in classical, let's forget the point of point.
I see.
You count the query in the same way, right? One query, just one.
Well, my guess is if you intentionally mess it up, then it matters. Otherwise, that's easy to do. That's my guess.
Sorry, what?
My guess is if you do a random oracle proof, I mean classical one, if you intentionally mess it up, then the K factor will also.
I mean, I don't think it's intentional.
That's easy, right?
I don't believe it. That's why.
I
feel it's just too different formally now, but
yeah. Like the domain separation is how you achieve having multiple oracles in application. Yeah. I'm not sure if that gives you the same bounds. I could check later.
You're asking about a great question. So you said that's easy. That's not trivial. So that's not well-defined question to argue.
Oh yeah, this is no, it's not non-trivial even in the classical case. Like it's surprising actually because I think kids has some textbook, and in the beginning they were using just one oracle, but like later they changed to multiple because that could be some better bounds, I suppose.
So that's my
yeah.
To mess it up, we are here.
Anyway, I'm not sure if it is
totally informal.
Let's see.
So I guess the process is that you
have
a mess it up.
But I feel like, yes, I think I don't see any reason it'd be messed up in the classical case immediately. It's just like in the quantum case, like because of these situations. Yeah.
If you use the domain separation point of view, like every classical, every query is just an index.
Yeah.
Then
exactly.
If you take that point of view, if you can achieve the same classical bound, it's almost trivial to make it post-quantum. We just use measurement program. Because it's not one oracle. Measurement program works for this perfectly. I don't see like what would be the technical challenge.
Oh, okay. I see. It's not the most challenging part. It's just that like the fact that you can't use query like the moves as your query bounds. You need to consider like the query weights to each oracles as something that could be like non-integral. Because of these kind of situations, it's just like a small detail. If you
then you are basically saying all the differences actually coming from the superposition query, not the number of different oracles. For example, even
no. But it's like superpositional query across oracles.
Yeah,
Yeah.
My point is, if you take the domain separation view, you don't have this problem at all.
You still have superposition problem.
Yeah, because machine program handle this automatically. So your index is also a part of the query. Your model automatically allows every query iteration, including the index. So that should be handled automatically by machine program.
Yeah, this is kind of it's basically sorry, this is not extremely. It's just to clarify that what we draw is not the reality, but yes, we do something similar to how this is done with the index and yeah. So exactly how is this implied by, so the PQSR definition implied by the round-by-round soundness, and the round-by-round soundness being a classical property that is easier to deal with. So like this is, we would like this implication ideally. So now we look at the proof. So first I see the classical case. So recall the definition of round-by-round soundness. We're first gonna label every partial transcript as either doomed or not doomed. Doomed means that it's almost impossible to make the verifier output a yes instance, or not doomed means that it is promising to make the verifier output a yes instance. So the round-by-round soundness says that to go from doomed or not, you can only go from doomed to not doomed with an additional verifier randomness in the next round with small probability. And in order to win the SR game, the prover will need to find a transcript such that initial instance is a no instance, but verifier outputs an yes instance. So it needs to, X is a doomed instance, but then the verifier outputs a not doomed instance. This means that you would like X to be doomed, but the whole transcript becomes not doomed somehow. And let's see how this transcript is constructed. So you're first starting with a doomed instance. And with an additional proof string, it stays doomed because the IOR prover is information theoretic and it can always pick the best proof. And if it was doomed, it will stay doomed. Then with the next verifier with verifier randomness, it only becomes not doomed with probability epsilon. Otherwise, it stays doomed. And then it stays doomed. And then again, it jumps to the not doomed with small probability with row 2, and so on and so forth. Notice that this looks very much like a search problem for some sparse set. So it looks like in order to win SR game, the prover will need to find some transcript that jumps from doomed to not doomed. And this is going to be sparse, which is guaranteed by the R/R soundness. From this state assertion prover, we can then construct a search adversary easily that finds something that jumps from doomed to not doomed in the ith round. And the solution should be this kind of thing should be epsilon sparse. And the search adversary, it will run the state restoration prover, and then it will compute the row 1 to row k itself at the end after the prover outputs its classical output. So it makes T plus k classical queries in total. And classically, this with the T plus k queries, you could find find something in this sparse set with probability at less than T plus k times epsilon. Yes.
Here, which set is sparse?
So it's the set that jumps from something that's doomed to not doomed. And it basically includes, it could happen in any of the rounds.
Yeah.
So it's any partial transcript where you find a point that it jumps from doomed to not doomed.
What do you mean by find? It's a it's a probability distribution. It can jump at every point.
Yeah.
What do you mean by found?
So the relation is just any string of this form where this part before the last verified randomness, here you're still doomed, and here you're not
You
doomed.
just need to find an I such that you can compute row I from the prefix.
It needs to find the whole thing, not just the index. It needs to find the exact
thing in red and in green.
Yes.
I see.
So it's basically derived from how state resolution prover could win the game. So you want to find, you can think about this as some search problem, like for any round by round sound IOR, you can think of the way to win state resolution game is to like win some search problem in the sparse set.
Then your solution A is to run this for P to compute row 1 to row K, and then how did you already explain how to find this solution from row 1 to row K?
So it means that if PSR is able to find such a such something that wins the SR game, so like it means it has found something that goes from doomed to not doomed, you can construct an adversary for the search problem. But the problem,
which search problem?
The search problem for this, the problem is that the adversary only outputs something like this at the end. Even though adversary itself knows the rows, the search adversary still needs to compute the rows itself. So that's why you have like even though maybe the state resolution prover already made the queries, it's going to like requery again. So and at the end, it makes all the queries that PSR make, and at the end it gets this as output. So it still needs to compute all of the row 1 and row K for the final thing that PSR outputs.
But once you obtain this row 1 row K, how do you detect if which row I is the row I you want? Is this like you need to detect this?
Yeah, so you still need to compute if each partial transcript is doomed or not doomed. Here, I guess sorry, maybe this is confusing because this is only about the query complexity of the adversary, not the A is we care about the exact query complexity of A because that's related to the probability that it could find the transcript at the end. So this is about how many queries it's making. But in actual construction of A, it also needs to compute, but then computing these don't make any additional queries.
Yeah,
computing doomed or not.
Is that efficient?
Yes, it's such a, we don't consider, because it's not a random oracle query.
Yeah, but I mean, is your model like for the A, it can make oracle queries, but besides that, it's computationally unbounded.
I guess we would think about it this way.
So what's
but it's about security. It's not about efficiency.
What's A's output?
A's output.
A will output row 1 through row K, or it just output the solution. The solution. Yes, I'm asking if A outputs this, or A need to output this and this.
It should just output whether it found something or it doesn't find something, I guess. So like it's more like a honestly searching. So like it's checking whether the SR prover has.
The syntax doesn't match in the second to the last line. You are saying that A need to output the solution, which is the red color string plus the green color string. But at the bottom, you are saying A just output row 1 through row K. This doesn't match.
I guess this is in order to find such a thing, it needs to compute these by making queries.
Necessary. For example, as an adversary A, I can't just give you a solution without output the intermediate values row 1 through row K. Is that possible?
Sorry, what?
Is it possible that the adversary could directly give you what you want, the solution? When I say solution, I mean the thing you put in the yellow rectangle. I do not necessarily need to compute the intermediate row 1 to row k. It is necessary.
Oh, you mean you just accidentally find something without querying all of those? Yeah, is that what you mean? So like maybe it just actually no, it can't. Oh wait, so like in order to compute doom or not doom, you need all of the previous row i's too.
Yeah, but you don't need to run all the way to row k.
Yeah, that's possible. It's like an upper bound for the query complexity. Like maybe, from here in the second round, you already found a transition from doomed to not doomed. Then the A can just stop there. It can just say, I found it. Then you only have like maybe T plus 2 classical queries. But this is the worst case. It will need to compute all of it.
Okay.
Yes. Okay. Now, so what happens in the quantum case? You actually still have the exact same search problem. So we want to find something from this of this form. But now the adversary have quantum queries. With the quantum queries, search becomes faster because we have the Groover's algorithm, which gives you quadratic speedup in searching. And maybe you've seen Groover's algorithm in form of this before, which tells you that you could find the preimage of 0 to the r. Actually, it's also true if you want to find the preimage of a set S. And Groover's algorithm can do this with probability at least t squared times the sparsity of S. And the first version is just a specific case of this, where you set sparsity to 1 over 2 to the r. But also there's also a limit to this speed up. So Groover's optimality tells us that you can't expect to do better than quadratic speedup, and this is why. So it's basically saying that Groover's algorithm is the best that an adversary can do, which is why this kind of tells us that our bound is somewhat tight, and we shouldn't can use this as an intuition. So now coming back to our problem, we're actually not exactly searching for a row I in a set, as the Groover's algorithm is usual version of Groover's algorithm. So we're trying to find some Q and Fi of Q such that this whole partial transcript is in a relation. And actually Groover's optimality is also true for finding something in a relation. And furthermore, our search problem is actually different due to the fact that it depends on the previous row i's. So this relation also depends on what the the previous oracles, as it's parameterized by the previous oracles. So like when we're analyzing for Fi, we fix the previous oracles. So then it's equivalent to searching for something in a relation R prime, and that is an epsilon sparse relation. So like this is not entirely precise because we're proving using instability lemma from CMS 19, but it's still like this is not the hard part of the paper yet. And sorry, I think so it's fairly standard, but yeah, this is like more of an intuition of how we did this part of the proof. Now we'll move on to like the main result, which is the VC, how the part 2, how the VC error appears. So if you were lost in the first part, maybe this will be interesting. Now let's first also see what happens in the classical case. Yeah, so recall that we would like to prove BCS security from some post-quantum state restoration sound IOR. So we need to relate BCS and security and state restoration somehow. And therefore, it means that we need to construct a state restoration prover from the IOR prover, from the BCS prover, so that the probability that the state restoration prover we construct wins the SR game can upper bound the probability that the BCS prover fools the verifier up to some vector commitment error, which we will define. And this construction of the state restoration prover has like 3 steps. So it's going to simulate the BCS prover. And it basically needs to simulate all of the oracle queries that the BCS prover is making. So we need to know how it's going to answer the VC queries, how it's going to answer FS queries, and how it's going to derive the output from the output of the BCS prover. So for the first part, we're just going to, for the VC queries, the state restoration prover is going to simulate some database, and it's for any queries that it hasn't seen before, it's going to sample lazily, and otherwise it's just answers with the existing recorded queries from the database. And
yeah, vector commitment as an oracle. You are using this one.
Yes. Sorry, the vector commitment that uses some oracles. So it's using some oracles, yes.
Oh, I see. It's the Merkle tree.
Yes. We can always think about what I'm saying with the Merkle tree. It makes sense. And the how to answer FS queries. So for the FS queries, the BCS prover is querying using some instance X and a tuple of commitments each time. But recall that in the SR game, we are actually defining the queries to the FS oracle. We're actually querying the FS oracles with the extracted string. So we would like to, so the state restoration prover will need to first apply extract. So you get some use the extracted string to then query FS. And note that here extract actually also takes the input, the database of VC to perform the extraction. So in all commitment scheme, you need the VC database to extract the pre-image, but we will just like omit that in the picture. Then it returns the FS query response to the prover. So this is this is a naive approach, because actually the prover, it can query some different CMs with the same underlying message pi1, and this will allow it to actually distinguish whether it's being simulated by the state restoration prover or not easily, and it can like decrease its winning probability if it's being simulated. So we don't want this. And to fix that, we instead also hash the CM inside the FS queries. This means that our actual state restoration definition needs to include salt as well, which we didn't talk about, and we will continue to just maybe omit the salt. And finally, we need to know how to derive the output. So after the BCS prover output its output string, what the BCS verifier does is it first performs some VC checks, and then it runs the IOR verifier by answering its queries with nth. And the state restoration prover will then simulate by also extracting from CM. So it will, and then it will answer the IOR verifier's query with the extracted proof string. Okay, now to summarize, this is how we answer the VC queries, how we answer FS query, and how we derived outputs. And notice that how we answer FS query and how we derive output are the two the differences between the left and right picture. Is that good?
Nothing.
Yeah.
Now, what's the main thing you want to convey?
The main thing is that our goal is to connect the BCS soundness with the state restoration soundness.
We're just talking about the construction.
Yes.
Nothing but run the extract. That's all.
Construction, nothing but
extract.
Right. It's just some intuition about why the construction is this way. Sorry, like some reasoning. Yeah, exactly.
PSR from P.
Yeah.
Do you claim anything? Yeah.
No, not yet. Not yet. The idea is that there's some differences, and the differences are exactly the vector commitment error we will define now. So the differences between these two pictures is the difference in the BCS soundness and state restoration soundness. And we want to define some vector commitment error that captures the gap between these two. So yeah, reminder that this is the goal. And so we want to capture the difference with like the VC error. And the first difference is in how you answer the FS queries. Actually, like you can view extract and FS as one oracle. So to the adversary, it's just querying an oracle to get the FS query. And the first property, which we call online consistency, says that an adversary can't distinguish between whether its FS queries are answered either without extract or with extract. Yeah, and the second difference is in how the IOR verifiers queries are answered. So again, we have the second property, which is offline extractability, is saying that these two are in close. So like no matter if you are answering IOR verifiers queries with ANS or with the extracted proof string, conditioned on the VC check passes, the two are close. And now finally, what happens in yes.
What you did previously is saying that for the notion of vector commitment,
yeah,
it already has a knowledge error well defined for that, right? For the primitive itself.
Yeah.
But you're saying
you can view it
that's
this
not
way.
That's not enough for maybe for this particular application. So you basically customize a new definition for within this framework. That's what you define as it's only C. Is that correct?
I think the previous definition is sufficient to prove this. It's just this, you can view it in this way, which is closer to our quantum definition. So like previously, the VC extractability definition, it has some
like the vanilla definition.
Yeah, vanilla definition, it works. It gives some proof
in the classical setting.
But I'm just
no definition to make your quantum proof more.
Exactly. It doesn't look like this, but it's like very similar to our quantum.
Can go to the extractability one.
Extractability.
I think the indistinguishability one is
that's more quantumly. Yes.
But what's your extractability? Yeah, difference two, I think. Next one.
Yes.
I don't understand what's this.
So it's in how you're deriving output, but this is actually the one that's easier to prove because the final proof strings are all classical.
Oh, I mean, I don't understand what it is.
Sorry. Yeah, so its difference too is in the, I guess what's easier is if I show. Yeah. Like it's how you're answering, so in the BCS verifier and in the FS verifier, they're both simulating the IOR verifier, but they're answering its queries differently. This one is answering it directly with whatever the prover outputs, a BCS prover outputs. But here we are using the extracted proof string to answer.
Oh, okay.
But also previously, like how you up to this point, how provers query were answered is also different. So like in the exact property, you basically allow some superpositional query to FS oracle. To the prover can make that and you can extract and then you have
instead of defining what does extraction mean in the Pono setting, you just define it by its functionality. Like I extract something to do these two tasks, so I define it to be secure as like as long as you do not violate these two properties, then I define that as a security of my VC.
Exactly. Yes. Though but then it is nice since that. Well, we still think that it gives classical intuition because you could state the classical VC property this way. And now is that was in the quantum case. Well, it is very similar. We need to answer how you're going to answer how you're going to answer VC queries, FS queries, and derive outputs. So here the extractor will need some trapdoor information about the adversary's query in order to extract the pre-image. And we use this compressed oracle as usual. But as we all know, that's only the starting point. So there are many more difficulties. Even it's not a solution. It's just a starting point. It gives you some quantum database. But we need to take additional care to simulate the BCS prover so that it doesn't cause much disturbance. And the VC queries is as we just answer the prover's queries with the database register with the compressed oracle, as usual. And for the FS queries, since we want minimal disturbance, we are going to run everything coherently instead of measuring the database. So the prover now can make superpositional query and get back answers of superpositional answers. And we use this U extract, which also takes in the database register, and it's basically a coherent implementation of the classical extract algorithm. So this is the classical extract algorithm, and it's just implementing it coherently with the database register. Then the state resolution prover will simulate BCS prover, run U extract on its superpositional queries, and then query FS oracle with that. Then it uncomputes with U extract dagger. So here, I'm also omitting the database register. Then finally, how we're deriving output is it's very similar as what I explained before. So we're using the extracted outputs to answer the IOR verifier's queries. Now, here's the summary. This is how we answer quantum VC queries, quantum FS queries, and finally how to compute the outputs. Yeah, it's very similar picture as before, and we notice the difference. There's not much new things to it. Yeah, and exactly these two differences is going to constitute our VC multi-extractability definition, post-quantum multi-extractability definition. So the first difference is in how you answer FS query. We have this as the other oracle with a U extract. So online consistency says that adversary can't distinguish between these two cases. And the second difference is, as before, the offline extractability, almost nothing changed. And finally, why is this the right definition for VC post-quantum extractability? So first of all, it's similar to the classical VC extractability definition. And second, it is strong enough to prove that BCS is post-quantum secure. There are a couple of caveats here because, as I mentioned, actually IORs also include oracles in these instances, and that fact means that it actually requires additional VC properties that I haven't introduced.
Can you go back to the previous slide? There's one important point I think needs some explanation. So this game differs two game. Do you take the measurement, like the randomness introduced by the measurement to generate this pi I into consideration when you're talking about the indiscriminate field? I mean, this pi I is not deterministic. Every time you measure, it's a distribution.
I'm not sure what that means. So
your pi I, if you go back to your PSR compared with P, in the post-quantum settings. Yeah, you see the pi I is obtained by putting a measurement there. So this measurement like introduced randomness.
Yeah. Oh, but it is all about probability.
So we are talking about that indistinguishability. You take this probability into consideration.
Yeah.
You are not going to fix the pi I.
No. It's a probability that when verifiers queries are answered with pi I, the extractability error is described by whether pi like if VC check everything is probability.
Okay.
It's not.
You need to argue that either you need to use something like
or
you need to count the weights.
Yeah. It's considering the randomness. Yes, this is an extremely simplified notation. And there are more challenges than what I'm just mentioning because we actually require extra VC properties to prove for IOR for this exact reason. And for knowledge soundness, since it's stronger than soundness, you also need the VC property to be a bit stronger. And we could get to that later. So the last question we need to answer is if any vector commitment scheme actually satisfy our definition. And it turns out that Merkle tree does. I think I don't have much time, so maybe I will skip that part.
In the quantum setting, Merkle tree does?
Yes. Also, it satisfies post-quantum.
Then what's a non-technical tool you are using?
So we have some new technical tool, actually. So we we have a new technical tool called it's using instability, but we have a new generalized instability lemma because the previous instability lemma is about like binary partition, and actually our the extract unitary it doesn't give you a binary partition, and we're using we have a generalized instability lemma that works for some more general any partition, and if you can show that the probability for a database to be in the set PI with an additional query, it only becomes not in PI with small probability, then we know that basically U extract and any quantum query almost commute. And this includes like a lot more general set of unitaries.
Then how did you prove that? Like, how do you take care of that measurement? I asked.
That part is proved using instability, and it's actually like the normal, just the CMS, like the binary partition one works. It's like you define some property that captures.
Count the weights in your partition.
Yes.
In that way, it just works.
What do you mean count weights?
I mean, you have a classical proof.
It's with some hybrid proofs, like you change from whether you're using a database register to you first measure, and then it's with a couple of hybrids.
Yeah, the question is actually
in
a classical setting you will have a proof. Now in a quantum setting, the only difference is you can make superposition query, and then you measure that query to the database. I mean, some quantum tool is needed in this setting to take care of this. You are saying the tool is just a quantum, post-quantum in instability lemma.
Yeah, instability lemma. Yeah, that part is, I think, less difficult than the indistinguishability, online indistinguishability.
Okay.
Yeah, so I will jump right to the final takeaway. So basically, what we showed is that the BCS transformation is post-quantum straight-line knowledge sound in the quantum random oracle model if the underlying IORs only satisfy a weaker variant of round-by-round knowledge soundness. And our proof analyzes the error from FS and Merkle tree separately through an intermediate notion, like the post-quantum theory solution notion, mirroring the classical proof. Yeah, that's all. Thank you so much. If you have any more questions, I'll be here.
Thank you. Any questions? Yeah, then feel free to repeat. So for those who needed to kind of understand,